Okay, for the theta join, the C denotes a condition. So the condition used in the theta join, they can be very different in different formats. Beside the cells dot bar equals to bar name condition used here, we can also define some other conditions, right? So this is about theta join. And we can also have a very special case of the theta join, which can be denoted as equi-join. We say equi-join is a special case because for the equi-join, we specify the condition C in the theta join as some equinities. In other words, we require this condition to be some equinities. And the equi-join can be defined in a very similar way as the theta join. The main difference will be about the conditions. We do not allow some other conditions to be used here. All the conditions to be included should be some equinities. And the result schema will be the same as the product, right? And they may have fewer tuples than the products. And we can represent the equi-join as R1 equi-join with some equinity condition like A equals to B. A denotes the attribute from R1, B denotes the attribute from R2, and followed by this R2, right? This equi-join is the operator between R1 and R2. We will also introduce another join in the following pages. It's called natural join. Actual natural join is also a special case of equi-join to be introduced later. And not all research has been done on joins for database systems. And the main focus and the target will be to do the joins among tables in a very efficient way. So there are so many papers on this topic in academia. And this is about equi-join, right? Equi-join is very easy to understand, and we can just define it in a similar way as theta join we showed before. And then next, let's go to another join. It's called natural join. Natural join is slightly different because for the equi-join and theta join, the schema of them, they are both the same as the product of the two relations. I mean, schema of the product, right? However, for the natural join to be introduced here, they will be very different. The given two relations R1 and R2, we can denote the natural join between them as R1 join R2. For the join here, we have no conditions, we have no subscript. It's just a join. If so, then we can say this is a natural join between two relations. So R1 is a relation with A1 to AN as the attribute. R2 is a relation with B1 to BM as the attribute. Then how about the output? We know the output will still be a relation, right? Then how about its attributes? It will be different from the theta join and equi-join. Before we say that for the theta join and equi-join, the attributes of the output will be A1 to AN combined with B1 to BM, right? However, for the natural join, we can represent the attributes of the output relation like S as C1 to CP. What are them? Actually, C1 to CP equals to what? Equals to A1 to AN unions B1 to BM. You can see the difference. Before the theta join and equi-join we showed in the previous pages, the output relation will be A1 to AN combined with B1 to BM, right? The total number of attributes will be N plus M, right? However, for the natural join here, the number of attributes will be P, right? P equals to what? Will be equal to the size of A1 to AN unions B1 to BM. If we have some common attributes between A1 to AN, B1 to BM, then the number of attributes in the output relation, the P, will be smaller than N plus M, right? So this is about schema. And how about the data tuples or pairs in the output? So in the operation, we will combine all the pairs of tuples from R1 to R2, which agree on some join attributes. What do I mean by the join attributes? Because we didn't specify any attributes in the join, this operation here, right? Actually, this operation will find the join attributes automatically based on the important relation schemas. And formally, we can define the join attributes between R1 and R2 as A1 to AN cap B1 to BM. So this operation can find the common attributes between these two relations automatically, and also do the joins based on these common attributes or the join attributes. So you can see the difference, right? Then you may also wonder, how can we represent this kind of natural join with some basic operations we defined before? Will it still be the same as the Theta join and Equi-join we showed before? Actually, it will be slightly different. Let me show you how to define as a natural join based on the basic operations we showed before. And we can provide the formal representation here. So formally in this system, we have two relations. We have R1. R1 has attributes like A1 to AN, right? And we have another relation R2. It has attributes B1 to BM. And the question will be, what is and how to define R1. Let me copy the join operation we get from the web, and we can denote it as R1 natural join R2, right? So we know the natural join definition will be different from the Theta join we showed before, right? So for the Theta join we mentioned, right, it combines two tables together by using the product first and then use this selection, right? For the natural join, it will be slightly different, right? And let's assume we can represent the output as a S, right? And let's assume we get the attributes. Let's assume we can represent the output as S relation. S has the C1 to CP, right? And we also get the join attributes as like we can represent it as like a D1 DQ, right? It equals to what? It equals to A1 to AN cap, right? It equals to A1 to AN cap B1 to BM, right? Let me change this format. It's 40, right? Okay, then how can we define this R1 and R2, the natural join between them? First one, it is still based on the product, right? You can still calculate the R1 times R2 first. Then outside it, we still have the select, right? We have select. Let me get the sigma here. We still have a select. What will be the select we have? We will have this. The condition for the selection will be what? The condition for the selection will be we have this R1 dot D1, right, equals to R2 dot D1, right? And let me get this one as a base case. Right. And R1 dot D2 equals to R2 dot D2, and blah blah blah, right? And R1 dot DQ equals to R2 dot DQ, right? So the D1 to DQ denotes the shared join attributes between these two input relations. Is it enough? The answer is no, right? Because for the C1 to CP in the output relation, they don't equal to the combination of A1 to AM and B1 to BM, right? We mentioned the C1 to CP, they equals to what? They equals to A1 to AN unions B1 to BM, right? In other words, the output schema will be slightly smaller than the combination of these two input relations, right? Therefore, for this definition of natural join, besides the selection, we need to further do the projection here. We can copy the pi here. We denote the pi as the projection, right? We further do the projection to select a bunch of attributes. What are the attributes we're going to select? Yeah, the C1 to CP, right? Therefore, we do further projection here, C1 to CP as to get these attributes, and we can just represent them as a subscript. I hope you can follow me, right? So for the natural join between R1 and R2, inside it we still calculate the product between two relations. It is necessary, and we also do this selection. And the selection is based on the join attributes. We want to ensure that the data tuples on the shared attributes are equal to each other, right? And besides this, we will do further projection to get the attributes C1 to CP. Therefore, the output relation, the schema will be S with C1 to CP. And for data tuples, they will agree on the join attributes. By default, right, the value should be the same between the same attributes shared by this R1 and R2. And let's assume we have a very special case. If given two relations R1 and R2, and all the attributes inside between them, they are all different. They are all different. If so, if all the attributes between them they are different, then this D1 to DQ will equals to what? Because all the attributes are different, and the intersection between them will be an empty set, right? If all the attributes are different, the union between them will equals to what? C1 to CP equals to A1 to AN and B1 to BM, right? Therefore, if this R1 and R2 they share no common attributes, then the natural join between them will be equals to what? In other words, this selection has no function anymore, right? It is useless. It will be similar for the projection. The projection will project all the attributes, right? It is useless neither, right? Therefore, if R1 and R2 they share no common attributes, then the natural join between them equals to R1 times R2, right? But this is a very special case. And normally, if we use a natural join between two relations, we assume they can share some common attributes, then this join will be meaningful, right? Otherwise, we just calculate the product. It is meaningless. Okay, this is a natural join, and I hope you can follow me. Okay, so we have an example on this page. Let's assume we have two relations. The first one is the employee, right? We have SSN and name as attributes. And the second one we have here is a dependent. It's another relation. We have SSN and dependent name. And we want to do a natural join between them. So according to our previous page, we show that between them we find them they share a common attribute SSN, right? And we can define a natural join between employee and dependent as inside it we first calculate the product, right? Employee product with dependents. Then outside we have this select employee dot SSN equals to dependent dot SSN, right? Because this one is a shared attribute between them. And outside we further do a projection. We project SSN, name, and dependent name. Because this SSN is duplicated, we only have one record in the auto-count schema, right? We have only one SSN here. And formally, we can represent the output of this natural join between these two tables as shown at the bottom. The schema is SSN, name, dependent name. We only have 3 attributes, right? Because this SSN is duplicated, we have only one record here in the auto count. And for all the data tuples, before we calculate the product, right, it will be 2 times 2. There should be 4 rows, right? However, we first check the condition. The employee SSN should be equal to the dependent SSN, right? Therefore, we have this record, this NX combined with this row crease remaining in the outcome, right? Similar for Brandy with David, as shown here. And the remaining ones will be removed, right? And first here we do the projection to only get the 3 attributes out, SSN name and dependent name. The redundant SSN will be removed, right, by its projection. This is about natural join. And besides this, we can also do a very general case, and we can try to calculate the natural join between 2 relations. Let's assume we have 2 relations as shown here. We have a relation R with 2 attributes, A and B. We have a bunch of data instances inside this table. Another relation we have is S. In the S, we have B, C as attributes. The B is shared with R, right? With C and C, they are shared attributes. Inside S, we have 3 data instances. We want to calculate the natural join between R and S. According to the definition of natural join, we know the calculation process may have 3 steps, right? The first step is to calculate the product. And we can try this example together. Let's calculate the product of these 2 tables first. And we want to calculate the product between R and S, right? And we can represent the table. We have 4 columns. We know this, right? As to the data tuples, we have 4 times 3, right? It should be 12. And we also need to have 1 row for the attribute names. Therefore, we have 13 rows, right? The first step will be calculating the. Let me write down the steps here. Step 1 will be R times S, right? So by doing this step, we can have the attribute name first, A, B, B, C, right? And we know the first row denotes the attribute names. Therefore, we have this highlight. We have a color for them, right? And inside this tuples, we will combine each rows in R and each row in S, right? Therefore, we have this X, Y, right, combined with Z, U, right, and V, W, and Z, V, right? And this 2 will be the same, right? So this is for the first X, Y. We combine with all the tuples here, and we will combine X, Z with the ones we show here, right? Therefore, we have the remaining rows. But here we need to change this Y to Z, right? Similar here, we need to change this one to Y, as well as this one to Z, and the remaining 3 rows, right? This one should be Z, this one should be V, right? Okay, so by doing the step 1, we calculate the product between them. We can get a table like this, right? And besides the step 1, we do the product. We also need to do the selection, right? We can just borrow the operation we use here, right? Or have the selection. Here we need to change this R with the B, right? Because the join attributes with B, right? Because they're shared by R and S. We know this R dot B should be equals to S dot B, right? They are the shared attributes. And we examine all the data tables we have. We check if this RB equals to SB or not, right? We check each row. This one, no, right? In other words, this row should be removed. We can just cross it first, right? Because this R.B is Y, S.B is Z. They are not equal to each other, right? They should be removed. How about this one? No, right? Remove this one as well. How about this one? No, right? And this one? Yes. This one? No, right? This one? Yes. This one? Yes. This row? No, right? They're different. This row? Yes. This row? No, right? They're different. This row? Yes. This row? No, right? So by examining all the rows, we compare the B attributes from these two tables to check if they are the same or not. This one should be removed. This one 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 removed. As well as the last one, right? They should be all be deleted. And by doing this select, we can get a table like this, right? For the remaining data we have in the table, they agree with each other on a B value, right? So this is the second step. Besides this, we need to do a further projection, right? We need to do a further projection by using the pi here. We know the join attribute is B, and the remaining attributes will be A, B, C, right? B is duplicated. We have only one record of B here. Therefore, we can have this pi as our style operator, and we have the pi works on this selection results. Let me change format. And we have the attributes to be a project with be A, B, and C, right? Therefore, for the table we have here, we need to delete one column, right? Either one or this one, it doesn't matter because they agree with each other, right? Whichever one we can delete, it doesn't matter. For example, we can delete this column here, and this one will be the result we can get by doing the step 3, right? And this table will also be the output for the natural join between R and S. And we can come back to slides and compare with them with the table we show in the slides. We have 3 columns and we have 5 data tables. Okay, let's come back to slides. This is the example we show here, right? We calculate the natural join between R and S. We also do the step-by-step for you in the example. This is the result we can get. It is the same as the one we showed before. I hope this example can show you how to calculate the natural join between 2 relations. And you can also try this, to calculate it by yourself on papers after class. It will be helpful for you to have a deep understanding about the natural join.